So, while it might take a lot of work to find the actual delta S for a reaction, we can often predict the sign of delta S just by looking at the phases of the reactants and products. So remember that gas molecules have a much higher entropy than liquids or solids. So for a reaction with gas molecules, all we have to do to predict the delta S is just look at which side has more gas molecules. So in this reaction, we have a solid forming a solid and a gas. So obviously the products, since they have a gas, they're going to be at higher entropy, and therefore delta S is positive for this reaction. And so really all you're looking at is which side has more gas molecules. Okay, so the third law of thermodynamics, the last one, says that the entropy of a perfect crystal at 0 Kelvin is 0. Because, a perfect crystal is all, orderly and aligned, and at 0 Kelvin, we have almost no movement, almost no random movement of the molecules. So this basically just defines what 0 entropy is. And so after we define what 0 entropy is, then we can assign every other molecule an absolute entropy value based on this reference point. So, you can find these standard entropy values of each substance in a table in a textbook or whatever. And so we can use these to calculate the entropy change for any reaction, similar to how we can calculate the delta H for any reaction by using the standard entropies of formation. So it's the exact same thing. We just take the sum of the entropy value times the coefficient for the products minus the same thing for the reactants to get the total delta S for the reaction. And so, as we'd expect, if a molecule is more complex, then it's going to have a greater standard entropy value because the molecules with more complex structures have more ways to randomly move around. So the value of delta G for a reaction, in addition to telling us whether or not the reaction is spontaneous or not spontaneous, it can also give us a lot of information about the equilibrium position of that reaction. So, if delta G is negative, obviously that means the reaction occurs, and so the more negative delta G is, the further to the right the reaction will be to reach equilibrium. If delta G is positive, that means the reaction does not occur, so the equilibrium lies further to the left. So, we talked about delta G equals delta H minus T times delta S. So another way to calculate the free energy change for a reaction is to use the standard free energies of formation, which are the exact same thing as the standard enthalpies of formation. And the formula is exactly the same. Delta G for a reaction, you do the sum of the formation delta G times the coefficients of the products minus the same thing for the reactants. So notice how we can use this products minus reactants business for all three thermodynamic functions, delta H, delta S, and delta G. So if you've noticed, most of the times we've written delta S and delta G so far, they've had that degree symbol, which remember means everything is at their standard state. Well, what happens if it's not at standard state? So free energy changes with pressure and concentration. So if the reactants and products are not at standard state, which means they're not at 1 atm and 1 molarity, the value of delta G will be different. So to calculate the value of delta G, we use this formula. So the delta G at this new pressure or concentration will equal the regular delta G when at standard state plus the gas constant times temperature times ln of Q, where Q is the reaction quotient if you remember back from equilibrium, and that's the concentrations of all the products over the concentrations of all the reactants raised to the exponent of their coefficient. So this formula accounts for the differences in delta G when we're not at the standard state. Okay, so next we're going to be looking at the equilibrium point of a reaction from a thermodynamic point of view. So the equilibrium point occurs at the lowest value of free energy available to the system. So spontaneous reactions, they have negative delta G, which means as the reactions occur, they're always losing free energy. It's always decreasing if it's negative delta G. And then eventually, it's not going to decrease anymore. And well, you don't want to increase it because the positive delta G means non-spontaneous. So it just sits there. And at that point, delta G equals 0. And that's the equilibrium point, when the free energy of the reactants and products are equal. So we can find when this occurs by using this equation and setting delta G equal to 0. And then we move things around and we get that the standard state delta G at equilibrium is equal to negative RT ln of K. We just replace this Q, the reaction quotient, with K, the equilibrium constant, because it's at equilibrium. So this relates the K and the delta G at standard state for any reaction. So just remember, delta G equals 0 when the system is at equilibrium. Okay, so the last thing we're going to look at is sort of more on the meaning of free energy. So the change in free energy, delta G, also represents the maximum possible useful work that we can obtain from a process. And so basically free energy, what is free energy anyways? Well, it's basically the amount of energy that is free to do useful work. Some energy we can use to do work, some energy we can't use to do anything. So when delta G is negative, that means we're losing this free energy, which means we're losing this energy that's available to do work. So if the delta G is negative, that free energy that we lost, that was used to do the work. So that's why delta G is equal to the work that we can do from a process. So since all spontaneous processes have a negative delta G, that means we're always losing free energy. So this energy that's useful is always converted into less organized and less useful forms of energy, such as thermal energy. For example, thermal energy, if a room is really hot, all the molecules in the air are bouncing around really fast, no matter how much thermal energy you have, you can never use that thermal energy to open a door or open a bottle or whatever. It's kind of useless.